Okay, let's get started. So today we will talk about Shellcode. So last week we learned how to override the return address for functions. So those return addresses they are stored on the stack and it's part of the memory, right? So when we have a memory corruption attack, memory corruption vulnerability, we will be able to override the return address. We can write it to anywhere we want. So in the examples we had last week, we have something like print flag function or print secret function. So that's where we return to. But obviously, if you are hacking a real world software, the developers will not give you convenient functions like that, print secret or print flag, right? So today we're going to learn how we can inject our own print secret or print flag into the address space and return to there. So this is the example program we will analyze today. Very simple program. Main function calls Overflow, the vulnerable function. After Overflow returns, it calls printf, I pity the fool. And Overflow is also super simple. There is a buffer, 40 bytes. Then there is a gets function. Gets will take input from the standard input std in, and it will end at a new line. So if your input is very long, then this function gets will put a lot of bytes in the buffer. But the buffer, at least at the Shellcode level, we are only asking for 40 bytes, right? So because of that, so clearly there is a buffer overflow. We can overwrite from the buffer to anywhere has a higher address. We can override that. So to pull off this attack, there are basically three elements we need. The first one is how do we override the return address or add a return address, right? This is something already learned last class. As long as we have data big enough, and as long as there is a vulnerable function like a gets, read f-read, then we will be able to string copy. We will be able to copy data longer than the destination buffer. Then we will be overwrite something, right? Then what do we overwrite it? So in the last class, we find the address of print flag or some instructions in the print flag or some other function print secret. So in this class, we don't have those addresses anymore. So we also need to decide what we want to overwrite. So technically, you can overwrite whatever you want, okay? So there are other tricks we can play besides what we're going to learn today. Then after we overwrite that return address, eventually we're going to execute some instructions, programs at that address. Then what code, what instructions should be there? So previously that's just print flag function. Now we don't have that. So how do we create that in the address space? So this is a simplified diagram of the stack. So the buffer is somewhere here. Of course, this is simplified. There may be other variables here. Then usually we have a saved EBP or saved RBP, 4 bytes or 8 bytes. And the EBP points to here. When this function executes, then the return address will be 4 bytes or 8 bytes higher than that. So in this particular example, inside the Overflow, this return address, if we do not override it, it should be a valid return address in the main function, right? That's what we already know. So when we override from here, we can override everything has a higher address than this, including this part, right? So we can control what and how to override the buffer. So we can override this, override this. So in last class, we didn't care about this part, right? We just put some garbage here. This part, we also put garbage here. So this part, actually in 2 weeks, we will learn we're going to utilize this when we do not have access to this one. And this is what we override. So now what we can do is, in this class, is we want to inject some shellcode into the program. So one way to do this is we put the shellcode in the buffer. Okay, shellcode is a piece of code that can give us a shell or return us the flag. Okay, something like that. So if this buffer is, because we can override from here, right? If this buffer is big enough, we can put the shellcode directly here. The problem is maybe the buffer is not big enough for us to put the shellcode. Another problem is this is stack. We don't really know the address of this, right? At least at a compiler time, static analysis, we do not know the address of this. This is different from last class when we do print, when we return to print flag. It's easy for us to find the address because that address is not on stack. It's a part of the code, right? This one is a little bit harder to find out. Also, because it's a little bit harder to find out this address, what we can do is we can put a lot of null operations in front of this shellcode. Right? The idea of this is if this part is really, really long, and each instruction doesn't do anything useful, there is a specific null instruction, and there are other instructions that is equivalent to doing nothing. Right? For example, the year X is already 0, then we keep moving 0 to year X, then basically we're not doing anything. Then if we jump to any of those bytes, then it will keep executing. Eventually, it will execute to our shellcode. Right? That's the idea. So obviously, this is not the only place we can put our shellcode, because we can override everything above, right? And here, this part may be too small, maybe not very convenient, maybe not enough to give us a huge null. So we can also put the shellcode at a higher address, right? To put the null at a very higher address, higher than return, after return. So this part we don't really care. But this way we can put a huge null there. So yeah.
Actually get a definition on shellcode, not a term
This what?
it's not a term I've bumped into yet.
We are going to talk about shellcode.
Okay.
Yeah. So we're going to look at your first shellcode.
Okay.
We kind of talked about this in the background part, right?
Yes.
Yes. So here I'm giving you a piece of shellcode which is only 28 bytes, but actually it can be even smaller. Yeah.
Can you just like quickly explain again why we need to know?
Why? Why do
need them all?
Why do we need to know? The reason is this is stack. We don't know the address of this shellcode. So if we know the address of shellcode, let's say the example I gave you, 28 bytes, you cannot execute from the beginning. You have to execute from the beginning of the 28 bytes, right? But you don't know the address of that. Yes. That's why you put a lot of null instructions in front, then hope to jump to any of them.
Yeah.
Then you don't need to jump to the beginning of the law. Yeah.
Have to jump anywhere in between the last and then.
Yes.
automatically.
Yes, it will execute one by one, but none of those instructions does anything useful. So eventually it goes to the shellcode. So let's look at this piece of shellcode. And this shellcode is 28 bytes, but it actually can be even smaller, 25 bytes. This is not the shortest shellcode. I think if you go to this website, they have a lot of shellcode available there. There may be something 17, 18 bytes on x86. Yeah. But this one is very clear, so we can know what it does. And later we will say why we don't really need this. So this piece of shellcode makes two system calls. The first one is execve, which creates a new process. Not create a new process, replace the current process with a program. So basically executing a new program in the current process. So this is what you do if you develop a shell before, right? Your shell will make a fork, then do an execve, right? So the fork will create two copies of your shell. Then the child will do execve to run a new program. So we are doing the same thing, but when you develop your shell, you are developing in C, and here we directly write assembly code and make system calls instead of function calls. So let's take a look at this piece of shellcode, only 10, 12 instructions, one by one, right? So when we start, execute this, we do not assume anything, right? Because we may inject this piece of code into the address space. It could be any time during the life cycle of this program. So we do not assume anything. The first thing we do is we do an exclusive OR of EAX register. So after that, obviously, EAX will have the value 0. So after that, we push EAX, but here EAX is 4 bytes, right? Then we push EAX and assume the ESP is somewhere here. We don't really know the value, but it's somewhere there. Then we're pushing 4 zeros onto the stack, basically. There will be 4 zeros. After that, we push those 2 values, and it will be those 2 values. And they are actually in each byte is a ASCII, is a letter, right? So basically what we're doing here is we are creating a string here. We talked about this 2 weeks ago. We're creating a string, and the string ends with 0. That's why we're pushing a 0 there. Technically, we only need 1 0, but here we're putting 4 bytes. Right? So the string we're pushing there is just /bin //sh. And I already explained last time why do we have 2 slashes here. Okay. After that, we are moving ESP to EBP. So where is ESP before? ESP points to this string because we just pushed it. Okay. ESP actually points to the string, which means ESP has the address of the string. Then we are moving the address of the string to the register EBX. So we're setting up for the system call, and the EBX has the program's address. The ECX, we are moving EAX to it. So ECX is 0. So ECX actually is a third parameter for that function call, which is environment variable, maybe environment variable or parameter. So we do not really need anything. So we just give a 0, right? So it's an empty string. The EBX is the environment variable. We also give 0 there. That's it. So now we almost finished setting up the parameters for the system call. The last one is the system call number, which is B11 in this case. Then we move B to AL. So EAX has a value 11, which is the system call number. Then we make the system call int 80. So from here to here, that's 9 instructions. Those 9 instructions are replacing the current program with the bin sh program, which is a shell. Okay. So no matter what program you are executing right now, it will be replaced to a shell program. So what will happen if this one is successful? This system call is successful, then the whole program is replaced with the shell, right? So do we have a chance to execute this? We don't really have a chance to execute it because this whole program, including this part, is replaced, right? If successful. However, if this is not successful, then this Then this will return and keep executing from here, right? Then after this piece of shellcode, what we have? We will have garbage. We don't know what we have there, right? Then it will crash this program, right? So if as attacker, if we do not want to leave obvious traces like that, if we want to exit this program gracefully, we make another system call here to make the exit system call. So in this case, the exit system call has a system call number of 1. So we get EAX to 0 again, then increase it. Now EAX has the system call number 1, then we just make the system call. So it will exit gracefully. So as you can see that if you don't really care about that part, then you don't need those 3 bytes. That should be 3 bytes. And this piece of code is equivalent to those machine code characters. Those are basically its numbers. Yeah. The binaries. Now we go back to this example to say, how do we want to get a shell or get a flag using this? So obviously, the first thing we do is we read the disassembly of this program, understand its stack layout, how many bytes we need to overwrite. I assume you are already familiar with this, since you have done several challenges already. The first instruction, we don't care. This is setting up the stack. What interesting here is the first one, there is a call to Overflow function. The call here, Overflow takes just the one. Overflow, there's actually no parameter. Oh, this is Overflow, sorry. So this is not called Overflow, this is called gets. Okay. Gets has one parameter, which is the address of the buffer. And from there, we go back, say, oh, the EAX has an address because EAX was pushed on the stack. And EAX has a value of EBP minus 30 in hex, which means buffer is at EBP. This is the buffer. Buffer is at EBP minus 30 in hex. Okay. So 30 in hex is 48 bytes. Right. So now you know that. If we want to overwrite this, what we can do? We put if we want to override the return address, we need 52 bytes of garbage, right? Then then we can have the return address. So now where do we put our shellcode? We can put our shellcode here because our shellcode is like 25 bytes, 28 bytes. We can put it here. This is actually big enough for us to do that. Right? We can also put it up there, which may be easier because we don't know the address of this. That's a problem, right? So what we're going to do is we will first try to put it up there and have a huge knob select, okay, to increase our chances. Then later we can try to put it here. Then we need to try many more times because we cannot put it. So here, let's say this whole part is 52 bytes. We need at least 25 bytes for the shellcode, which means we have another 17 bytes for the knob. Okay, it's still very small. But if we put it here, we can put thousands of bytes of knob, right? 2,000, whatever we want. Okay, so even if we don't know exactly where the buffer is, we still need to put address there, right? So one way to do that is we debug the program, we figure out where it is. But when we debug the program, the address will not be the same as when we just run the program. Because when you debug the program, GDB is going to load that program into the address space, and GDB will push a lot of its own environment variables there. And that will make the stack address much lower than when you just run the program. The most important approach we use is actually just brute forcing. We just guess. That's also the reason why we want a knobs net. Okay, the knobs net will help us increase our chance of guess. So first, we're going to use this shellcode. The shellcode you just looked at. Okay, this is a 25 bytes, not the 28 bytes. I removed the last 3 bytes. And this is the command we are going to use. We are going to use Python. We first print out 52 bytes of garbage. Okay, we're trying to place the shellcode at a higher address after the return. So we have 52 bytes of shellcode garbage, then 4 bytes of the return address. The return address is supposed to be the address of the shellcode, right? Which we will figure out. We will figure out roughly where it is. Then we have a huge knob set. Okay, the knob set, the knob instruction is just 90 in hex, and it's 1 byte. Okay, so we can have like 1,000 bytes, 500 bytes of that. So after that, we have the 25 bytes of shellcode. That's it. We put it exactly this part. 25 bytes. You can see there is only one x88. That's int 88. So we're making only one system call. After that, we actually need to do a can here. This is not super important, but I give you a reading material there why we need this. Then we pipe the whole thing into the to the program. Let's see what we get here. So this is return. Return fork. So let's first debug the program. We'll run the program a little bit. Okay, the program doesn't give us much. It takes something from the std in. That's why if we give a long random string, whatever, it should crash the program. Right? Then we do a GDB, we debug the program. The reason we debug is we want to figure out where the stack is, roughly where it is. So I set a breakpoint at vol the B is setting a breakpoint. The R is running the program. Now we are at the very first instruction of vol. And if we do a P, ESP, then we can find out where the stack is right now. So when we are executing the very first instruction of vol, the stack pointer points to somewhere here. Okay. So we know that in GDB, our buffer will be somewhere near here, okay? So D656, somewhere there. Then outside of GDB, if we're just running the program, not using GDB, the buffer's address probably will be higher than this. But it's hard to tell how much higher. That's why we need to keep trying. Okay, so let's try to get our shellcode here. You can directly use the shellcode. So when I copy it, there are some errors. There is a 1, what one should? Oh, should be C1. Oh, yeah. So there's a white space. The new line becomes a white space. Anything else? Looks fine. Okay, fine. So we have this. So this 4 bytes of address, we have something like the higher 2 bytes are FF. This one is D656. So let's try to 60 D6, whatever. Address a little bit higher than that. Then let's put a big log step. Let's put maybe 500 bytes. And let's try if it works. We do this. Let's say it works. Oh, it actually works. Okay, we got the shell. We can execute command. But there is a problem. If I do who am I? So when I logged in, what was my account? I'm CDR. I don't have privilege, right? I cannot count the flag. But this is a set UID program. But I'm still CTL. Okay, I'm not root. That's a problem. Okay. So when I do a cat flag, I will get permission denied. Okay. So even though the program is a set UID program, when I replace this program with a new program with a shell, the shell doesn't inherit the root privilege. Okay. So this is actually a new feature in a later version of Linux. So previously, several years ago, when I taught this class, on some Linux versions, this will work. This will give us root privilege. Yeah. But we only need to change a little bit. So hold on, let me show you this. So why the lob sled is important here? Let's say the lob sled we have is much smaller. Or let's say we do not have an lob sled. When we do not have a lob sled, it means this address has to be the beginning of the shared, right? Since I just put a random address there, most likely it will not be. So let's see what we get. What? Let's see what's going on. We're really that lucky today. Yeah, we're really that lucky today. That makes sense. That's it. Wow, we're really that lucky today. So I put a random number there and it happened to be the address of the shellcode. Yeah. So if it's any other address, it will not work, right? Yeah. Any other address, it will not work. But so let's say, but if we have an offset here, we have an offset, then we change to another random address. So here was D6, which change to maybe DA. That's probably D6 to DA, that's more than 500 bytes. That's probably too much. Maybe D9, something like that. Yeah, that's D9 is probably too much, but we can make this one a little bit bigger. Yeah, okay. We'll put a random address here, which is much higher than the previous one, previous D6. You change one from 6 to 7, you are basically increasing 256 bytes, right? So here we're actually increasing maybe 700, 800 bytes, but our offset is 1,500 bytes. That's why somehow we hit the middle of our offset and eventually execute this. Okay, but this is not giving us what we want. We are not inheriting the privilege. So to inherit that, actually we only need to make 2 more system calls before that. Before we execute that new program, we need to retell the existing program on OS. My privilege is root. So we are making 2 system calls. The first one is get UID. So that one actually you can also use 0. To make it more general, sometimes you're not necessarily want to be root. You want to be another user. Want to be the user of the program, the owner of the program. In this case, it's root. So technically that one we can put 0. I think we can put 0. It depends on if the return value is that. Then we just set RE. RE means E means effective, obviously. R, what is R? Anyway, it's set REUID. So we set that again. That will be 2 more system calls. The first one is here, system call number 31. The second one is here, system call number 46. So after those 2 system calls, we run the same 25 bytes to run that exe cde. So this is a new. This is a new shellcode, a little bit longer. Copy this. Yeah, go ahead.
Instead of invoking a shell, you can use basically do a read system call.
We're going to do that next. Yes, you can do whatever you want, basically.
That way you don't have to use that one.
Yes, but getting a shell is more flexible, right? So you can run other programs. So there's a white space. Another white space. Here is a white space. So we put only 150 here. The address. 8, 7 will work. Okay. Okay, looks good. Yeah, we run this. Looks like we're getting a shell. Okay, we're getting a shell. Now who am I? Now we are root. We're not CPM. So now, if we can't, now we're getting a flag. So we create a new process. We replace the existing program, which is buffer overflow return 4, with a new program, which is the shell BSH. And the shell inherits the root permissions here. That's why we are getting this flag. Set UID. We are talking about this part, right? So what you need to do here is before you call execde, you need to make the system call to set the current UID to root again. Yeah, that's it. Otherwise, if you don't do that, otherwise the permission or privilege, they will be dropped. I do not really know which exactly point it was dropped. I never debugged that part.
Tell me code to process it. How is that? Setting the set UID, how does it set UID?
Exactly. I actually believe, I think the permission is probably dropped when the shell create when we type the command in the shell. So when we type who am I, or when we type cat, so who am I and cat, they do not have the permission. You know, they are, like you said, they are forked from the shell. But it's also possible that shell already doesn't have that permission. Never try to debug that part. Okay, so another question is, like you asked, sometimes we do not necessarily need to get a shell, right? Our goal in this class is to get the flag, right? So we can write a piece of shellcode just to get the flag. And this is a piece of shellcode to do that. And this piece of shellcode will not create a new process, or it will not replace the current process. And because of that, we do not need to use the set UID system call, okay? So this piece of shellcode actually executes in the address space of buffer overflow, that program. But still running as the buffer overflow program. Okay. In this case, what we have here, we are making, so how many system calls we are making here? The last exit 0 doesn't really matter. Okay. But before that, the first one we have is our open, right? So in the buffer overflow program, we're trying to open the flag file, and that program is a set UID program, so we will be able to open. After we open, then we send the file, send the content to one. This one here, that's the file descriptor, std out, standard out, which is terminal. So we'll send that. So this is a little bit different from what you program in Python or C. When you program in Python or C, you open a file, you read a file, then you write something, right? Those are 3 steps. You can still do that, but that is much more complicated. Here we only need 2 steps. Okay, so imagine you first open, then you read. You need to read the content of that file to a memory location, to a buffer. Then you need to write from that memory location buffer to the file descriptor, right? First of all, that's 3 system calls: open, read, write. And also you need a memory that you can write to. Okay, it has to be a safe memory. So in this case, we simplify that. On Linux, there is another system call called send file. By doing that, we don't need that read and write. We directly send file. So open will give us the file descriptor, and we don't need a buffer to store the content of the file. Then we just send the file descriptor to. So this one gives us the file descriptor of the flag. Then we just directly send that first in. Okay. So this is the shellcode. It's a little bit longer, but you can say this is the first system call. And you can see this part. This part is basically the string, right? And we're not pushing, before this, we're not pushing 0 there because it's already there, 0. So we didn't do that. So this is basically the flag file name. So this is open. After open, the file descriptor is in EAX register. That's why we're moving EAX to ECX. So ECX is the second parameter for the second system call. So after that, let's say here we're actually sending, oh, this one is, so here I put 1,000 here, but actually you can say, well, here is actually 100. Okay. 64 in hex is 100. So this value doesn't really matter because our flag is not that long anyway. So I believe this is the system call number. The BB is the send file system call number, and you can say BB is moved to AL, right? So after that, we make this system call. So actually, this is it. We don't really need this part. This part is the exit. So let's try to do this. There's a new line. There's a lot of line. So the buffer's address is here somewhere there. Which is 2238 FF. Let's have a huge long step. Okay. Then let's say, what else do we? The name of the programming change, like this. So when we run this, we directly get the flag, right? So like I said, the exit part doesn't matter, which is technically this part. Okay. This part doesn't matter. So what will happen if we remove this part?
Get a segment.
Yes, we are getting a segment fault, but for the previous one, what will happen if we, for this shellcode, if we remove this part, what will happen? Oh, this one we don't have an exit. Yeah. So here we are. Let's remove this part. Let's remove this piece of code. We're still getting the flag, but after we get the flag, the program continues executing at the end of the shellcode, then which will be garbage, right? That's why we're getting a segment fault. So we can debug this program a little bit to say where we jump to show you we're actually jumping to the middle of the knob state. And also use this opportunity to learn a little bit how to use GDB. Let me copy. Let me copy. We're debugging this program. We want to set a breakpoint at maybe just lawful. Now we want to run this program and fine with that. It works. Copy. Fire name Mula. Okay. Oh, this one was fire. Okay. Okay, that works. I need a 3 smaller than sign here, and all the input goes to the program. So we are in lawful. So let's set a breakpoint here. Gets from now we set breakpoint here. We will say to continue. So now we can examine what we have as the buffer, right? The buffer's address will be, let's examine 20 bytes. We know where buffer is. Buffer is EBP minus 30, right? Yeah, good. Buffer is a EBP minus 30. So if we examine the buffer, we'll use X. X should be X. So that's the value at the buffer. So nothing useful here. But if we keep going, we should be able to say the return address and parameters. The Overflow doesn't have a parameter, but there should be a return address. This one looks like a return address, or maybe this one, the return address. So now we are going to execute gets. We do not want to step into that. Instead, we will step over. So we use next instruction unlike. So now we are at this add instruction. So now the buffer should have been overwritten, right? So this is our buffer now. We put 52 bytes of garbage. Then we have that return address, right? It's our return address. So after that is our log. We have like how many? Thousands bytes of log. So if we do a 200 here, we are still getting logs, right? We put the 1, but if we put 2000, we will be able to say our shellcode after the log, right? So that's where the log ends, and this is our shellcode. Our shellcode is only 25 bytes or something. Which one was the maybe 20 longer than 25 bytes, but definitely not this one. So yeah, from this, I don't know what they are, but at least this part is actually our shellcode. Right. So now, where are we? So now we are going to set a breakpoint at our return instruction. So we continue. We are about to execute the return instruction. But before that, before the overwriting, we were supposed to return to the middle of main. Now we do a SI step in. We're supposed to go to our shellcode or somewhere in the middle of our log, right? And we go to this address, and it's not a function. So that's why you cannot do this symbol here, but you can still examine what is at that address. Let's examine 200 instructions. I means instruction at the EIP's address. And you can see we are at the beginning of our log step. And where does our log start actually? So let's say we minus 100 bytes. Even if we minus 100 bytes, we still get a log, which means we're in the middle. So then if we keep going, eventually we are going to hit our shellcode. In this case, when GDB debugs this program, it doesn't have the privilege. That's why it doesn't print out the flag, but just give us the segmentation point. So that is 32-bit shellcode. So then now let's look at how we do this with the 64-bit program. It's actually very similar. It's just the calling convention is different. In 64 bits, we do not use stack to pass the first 6 parameters. Instead, we use those registers, right? So when we make system calls, we also use registers as well. And the 64-bit version of the code will also look a little bit different as well. This is a assembly of the 64-bit version. And you can say looks like it's actually a little bit shorter. Right? So here we have gets. Gets where you get so this is 64-bit. So the first parameter or the only parameter of gets is not from the stack. Instead, it's from RDI, right? The first argument, like I put in the previous slide, the first argument is in RDI, the second is RFI. So that's why we're looking for RDI here, and RDI gets its value from RAX. And RAX gets its value from RBP minus 30. Okay. So in this case, the compiler actually gives us not the same size of buffer, which is 48 bytes. Then how much, if we want to override the return address, how many bytes of garbage do we need? Yes, exactly 56, right? Because in this case, the saved RBP is 8 bytes. So, and our shellcode can also look a little bit simpler in 64-bit because there is a system call command, and in 64-bit you can directly reference a string with the RIP. So the shellcode can be actually this short. So if you want to compile this, those are the commands you are going to use. But we're not talking about this today. Several weeks later, there will be a shellcode module, and we're going to talk about those.
Even with obviously a good connector coming in, figuring out all the stack, like there's some tools that can experience the stack.
Well, the tools you are referring to, they also need to look at the assembly, obviously, because at a C code level, some of you have been using Battery Ninja or Jira for your homework. So when binary ninja or Ghidra lift the program from disassembly to something look like a C code, some information is lost, right? Like how many bytes that variable is. Those information is only available at the binary level. Because when you compare that, like I said, you write a C code, you say in C code level, I want 16 bytes. You don't really know what the compiler does. The compiler can put 500 bytes there to make the program run faster or whatever. Those information is only available in the binary. So in 64 bits, the system call numbers have been updated as well. So now we are looking at system call number 59 here, which is EXE CDE. So this one is equivalent to the previous print flag shellcode. I guess this part doesn't matter, that exits. Yeah. So we can try this on 64-bit. So first the garbage is 58. Then the address is 8 bytes. Not sled, then the shellcode.
58.
56, sorry.
Okay.
Mhm.
Trying to figure out if I was missing some bytes.
So this one will give us directly the flag. Everything else is good. Okay. So if we run a program, like don't tell us if we're maybe try to get a rough idea where the stack is, the buffer is. Run a program. ERP. So that's the address. FF. Hold up. No, that's not. Should be WX or QX. The QX. Oh, should be RSP. Sorry. RSP. Okay, so that's the address. So not ESP. So that is the address. Then we can try that address, maybe make it a little bit higher. This one we 150 should be good enough. 1,500 should be good enough. So this one is 7F. 1, 2, 3, 4, 5, 6. So the highest, the most significant part is not 7F. 5, let's do maybe E7. Increase our chance. Then we have FF, 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 7F, which means the other 2 bytes should be 0. But because of 0, we may have a problem. 1, 2, 3. 1, 2, 3. Okay, that's correct. 7F. But because of that 0, we may have a problem, or there's a lot of, let's say several white space here. So this one, there's another one. Let's see if this works. Okay. And let's just type this into buffer. Oh, it works. So even if we have a zero, this one works. So this actually gives us a flag because we have a much smaller offset. Okay, I don't believe we're that lucky again. Let's try. No, lucky. Yeah. Okay. So this is the first one, which directly give us the flag. This one will give us a shell. So the same idea. So we're not going to do it. Instead, what we can do is we will go back to the 32-bit version because it's easier. The shellcode is shorter. We will try this one. So far, we have been putting shellcode up there and use a huge offset, right? Now let's challenge ourselves to put shellcode here. Now we only have at most 16 bytes of knob, which means we need to try a lot for the buffer address. But eventually we should be able to get it work. So that's where sometimes you need to write script to automate this process. Let's take a look. Which one is this one is easier. Oh, not this one. The one here. Which one is easier? Oh, there's no one new line. No, that's good. We'll go back to overflow return 4. So we could okay. So how do we change? There's another white space here. There. So now how do we change this? We don't want that garbage, right? What is this one? Is that an Etsy or? Oh, this one's long. This one's quite long. Oh, this may be 40 bytes, even longer. So this will be very challenging. We have to find the exact address for that, almost the exact address. Yeah, the previous one was talking about 25 bytes. So this one is like 40 something, so which means we almost have no log, maybe several bytes of log. Yeah, we probably do not want to do that. Yeah, well, we probably need to write a script to keep trying there. Yeah.
But it's very just for fun, right? That we don't need to.
Well, I mean, as long as you get a flag, why do you choose the harder way, right?
I also wanted to ask, like, will it work if the data is for the binary function or not in versus, but in the directly?
It still works. Usually the main function, the stack frame will look a little bit different than other functions. Not necessarily. You need to figure out. So the main function do not necessarily use. I don't remember. Some compilers it doesn't use EBP. Yeah. So basically you need to read the disassembly to figure out the stack. And that's why I deliberately use a vol function as you use a main function to call the vol function instead of directly put the vulnerability in the main function, because it adds a lot of layer of complexity there. Yeah.
Probably missing something there, but currently like jump to ESP plus something. Can't be right. The return address, the dynamic region, there's a not.
What do you mean by ESP plus something?
Like we want to jump to inside, like we want to jump to a specific address. instead of
Yes.
Providing the address directly and to ESP and then do something. They're not.
It is possible, but so basically you are talking about getting the address at runtime by doing some calculation, right? But the piece of code that getting the address at runtime, you need to execute that first. How do you execute that? You also need to the address of that, right? Yes. Yeah. Yeah, you cannot figure out the address of that.
Go back to the terminal. The previous one, the 64-bit one.
Okay.
Added 00, right?
Yes.
The address, but that would make a lot of. Because that is the random period. 00
No, because
because written in the zero.
so that 000 will be considered as end of a string. That's correct. However, the vulnerable function in this case is gets. Gets doesn't stop at the end of a string. Gets will stop at a new line, which is 08 instead of 0.
But I was asking about the return address part.
Exactly. Yeah, that's what I'm talking about. The return address you put 00 there. Yeah, but the vulnerable function here is not string copy. If the vulnerable function is a string copy, then you will not be able to get the shellcode, the whole thing exploit to the memory copy there, because there's 0 there.
But address was starting 7F. 7F should be at the last.
No. 7F is not the last. The address is 8 bytes. The 7F is actually at the 6 bytes. Yeah. Yeah. Got it?
It was
Yes. Yeah. You know, that's why we put 0 there. Okay, let's keep going then.
before you can for the project, your child will have this information, right? Unless the parents are also.
It's basically the design of OS. So when you write the OS kernel, you decide whatever. So some version of Linux, we saw that when you fork a process, or not necessarily fork. In this case, it's not really a fork. In this case, it's exe7e. When you do an exe7e, the new process will inherit the old one's permission. But on the server we're using this version of Ubuntu, it doesn't. That's why we need to redo that. Do that system call. Yeah. Some other versions may design differently. Okay, so we just learned how we can return to our shellcode. And there are several challenges there. First one is we don't know the exact address where we should return to, where exactly our shellcode is. That's why we use logs there. Second is the setUID program is replaced with a new image. The new process doesn't necessarily inherit the root privilege. That's why we want like getting a shell. We need to do that setUID thing. When we are not getting a shell, we are just doing read and send file. replacing the existing program with a new image. So in that case, we do not need to do that share SETUID. So now we're going to learn there are many other places we can place our shellcode. Just now we put our shellcode here in a buffer. It's one shot, right? We put our shellcode, we put our exploit those address at the same place. There are many other places we can put our shellcode. Technically, it's just a piece of code. And that piece of code must be in the address space of this program. Okay, and that address space must be executable. That's it. Okay. So the attack we just pull off, we need the following abilities. We first need to put the shellcode onto the stack, right? The stack must be executable, and we should have the ability to overwrite the return addresses on the stack before the return instruction is executed. And eventually we should have the ability to give the control to our shellcode. So sometimes, especially as an attacker, I like to list those kind of conditions we depend on to pull off attack. Okay. More conditions, the better. The reason we do that is we clearly list those, then we take out one condition, then we come up with a new defense. The defense can be very simple. We take out one condition, right? For example, in the previous example, the stack needs to be executable. Even if you are able to inject your code, shellcode to the stack, but the stack, if it's not executable, why the stack should be executable in the first place? It should not be, right? Because we're supposed to only put data on the stack, or put the code on stack, right? We're not supposed to. Then at OS layer, or even CPU layer, right? We make the stack only readable but not executable. Then we can defeat the previous attack. And that was a CPU feature introduced like 20 years ago. Okay, so if we take all this, now let's say we have the ability to overwrite the return address on stack. If we take all of this ability, then we can have a defense called stack clarity, something like that. Right? So we are going to do this kind of practice in this class a lot, especially the defense part. So next we can see how we can inject the shellcode in environment variables and also command line arguments. So we talked a little bit about this before. So how your main function is get called. The developer develops the main function. When a new process, your new process is created by the OS, the OS eventually gives yield the CPU to the underscore start function. Okay. So this is a function not developed by you. Okay. Compiler put the function there. And this function eventually calls the underscore libc underscore start underscore main. Okay. This is a libc function. We start with libc. So the start function technically is not part of libc because not every program uses libc, but this still should have a start function. Then eventually this start function, start main function, will call your main function, and your main function will call all many other of the functions you develop, right? So the reason I'm showing this is before your main function, other functions are already using the stack. And also they are preparing the stack for your main function and other functions, right? So in C code, as long as there's a function, then you need to prepare the stack. So this is what the stack looks like before the main function. We're talking about a C function. So I have an example code here is stack layout. I have the source code for that. Yeah. So the stack layout program will print out the will only print out the arguments for the main function, right? So the main function has 3 arguments. The first one is argc, which is the number of command line arguments. In this case, I type the name of the program with some random string. So that's why it has 2 arguments. That's why argc is 2. The first call here, I only type the name of the program. So that's why argc is 1, right? Then the second parameter is a pointer to some strings. And those are called the strings are slides. So the strings are argv 0. Those 3 addresses. Now the second are, let's say, where the yeah. So this is basically an array of pointers. This is an array of pointers. That's the second argument, and the first element of that array is argv 0, which is the command line arguments, the name of the program. Then we have argv 1, which is your second command line argument. If there are the third one, there is a third one, then there will be argument 2, right? So those are just address pointers, right? So eventually they point to string. So this one points to the program's name. This one points to the second argument. This one points to the third argument. And in this case, we can stand out hello world. There are 3 arguments. The second one is hello. The third one is world, right? So both of them are strings. So they are pushed onto the stack by the functions, by the function calling the main function, such as the libc start main. Okay. Because main function is also a function. To call that function, you need to push the parameters, the address for them onto the stack, right? So after that, we have the environment variable pointers, and there could be many environment variables, and each of them is a pointer, and their string is actually at an even higher address. So if we debug this program, so I think we tried this last time, but we didn't see the environment variables. Today, let's try to find the environment variables on this stack. So if we set a breakpoint at the main function, we execute this, then our two hundred bytes of EIP, ESP. So this is 32 bits. Yeah, 32 bits. So it's not too much. So from here, EIP, the ESP because we're at the beginning of that. This should be the return address. This is the parameter, right? The first parameter, which is one, because we only have one command line. Then those are other parameters. This looks like those are addresses, as you can see, and those are probably 7. So you can see those are pointers. They are pointing at stack address. And after the pointers, there will be a 0. After that, there will be other pointers. There's only 1. And those could be environment variables. So how do we examine the environment variables right here? Okay. We just invite strings in. So we'll do 200 strings from ESP. So we keep doing that. So this is E7. Oh, now we get the environment variables. See that? So we started examining from basically a random address and stack. Then we keep going to a higher address. And eventually we should be able to find the environment variables. Okay. This one is not environment variable, that's a command line. We have program name. So after that, we have environment variables. So maybe 300. So we say all the environment variables, they are on the stack. Like even user APF, those kind of stuff. So they are in the address space of this program. Okay. So the loader and other functions, they put those there. Which means if we set an environment variable here, we set an environment variable in the shell. And eventually that environment variable will be copied into the address space of the program. And that environment variable, we can do anything. We can put shellcode in, right? Let's try that. The command we use should be export something. Yeah, let's do export. Export. What will I say? Let's say NFL equals to, do we need a $sign? Oh no, we don't need a $sign. Okay. Deals with. So now we have an environmental variable, NFL. We do this. We can say it should be somewhere. It's here. Say, that's an environment variable. Now, if we go back to this stack layout program, we examine its stack, that environment variable should be there. Here, okay. That's the environment variable we set just now. Which means we have another place like to put our shellcode. We can put the shellcode in the environment variable. Right? So when we do that, the shellcode eventually goes to the stack. It's just a much higher address than before. Another thing is, if we put, instead of putting environment variables, we can also, let's say we run a program with those kind of random strings. And from beginning, those strings are command line arguments, right? And those command line arguments should also be placed onto the stack, because main function needs to use that. So it must be somewhere here, right? Which means we can also, even if the program you are hacking is not taking input from command line arguments, you can still put command line arguments there and put the shellcode there. It will be pushed onto the stack. It will be injected into the address space of the program. Okay. So now let's go to the next example. So how much time do we have? 20 minutes? Okay, I think we can do it. Okay, overflow return 5. This one has a very small buffer, 4 bytes. Okay, the compiler may give us 8, but usually the compiler will not give us 200, right? And there is a fgets, which is still vulnerable, but fgets is only reading 18 bytes. Okay. So our shellcode is already 40 something bytes. We're not going to get the whole shellcode into the address space by using the fgets. So if we look at the document of fgets, you will know that the fgets will only copy actually. So here is the number of bytes it's going to copy. It's actually not the number of bytes it's going to copy. The number of bytes it's going to write, I think. Yeah. So let's say in the previous example here, we have 18 bytes. fgets will only read 16 bytes and append a 0 and a new line and the n, and make sure eventually write 18 bytes, which means we can only include 16 bytes. So this one is carefully designed. I carefully designed this. This is a disassembly of this program. fgets is here. The buffer is at edx. You can say push edx here, and edx has edt minus 8. Okay, which means the buffer is only 8 bytes. Then you have 4 bytes of saved EVP, 4 bytes of return. That's 16 bytes. Then after that, fgets will write 0 and OA, or maybe A and 0. Yeah, maybe it should be this order, A and 0, which means you can only overwrite this. You don't have 8 bytes of shellcode. You can only overwrite the return address in this case. You can overwrite this, but we haven't talked about this part yet. If you use this part, you have 12 bytes. 12 bytes is not enough for us to put a shellcode here, which means you have to put shellcode somewhere else, right? In this case. So for this challenge, we have to put the shellcode somewhere else. And that's exactly what we're going to do. We're going to put the shellcode in environment variable first. Let's try that. It's okay. Overflow return. Another white space. Here's the white space. Here, one solid white. Okay, now we put the shellcode in an environment variable called scode. Obviously, the name doesn't matter. Let's verify if it is there. It's here. So many of the bytes are not printable. That's why we're not seeing it. Right? Then we can try to get the address of that environment variable. And I develop a tool here for you. Get environment 32-bit. Then you put the environment variable name here. It will give you the address of that environment variable. Okay. But this is a little bit tricky because the environment variable address you are getting from this program is the environmental address in this program. It's not necessarily exactly the same as a new program. A lot of programs. A lot of thing is the address you are getting here. So this whole thing, okay, this whole thing is a string. Remember that this whole thing is a string. Every other line is a string. So the address you are getting here is actually this address, which is not really part of the shellcode. It's a string S code. Your shellcode is actually at this address. Does that make sense? Yeah. So if you use exactly this address, it may not work. So our exploit should look like what? This is fgets. So we are going to get how many bytes of garbage? 16, right?
Oh,
12. Okay. 12 bytes of garbage. Then our shellcode address. That's it, right? Don't need anything else. Because the shellcode, when we run this, the shellcode is already in the address space. Then since we have a lot of knobs, so let's use just a big address, AA. So here we have EA there, then we just change to AB, maybe BC. BC should be good, I guess. Let's try. Okay, it works, right? So if you use exactly that address, EA, AB, even if this address points to that, it will point to here. And that's not a valid instruction. You are likely to get a segment fault or illegal instruction. Right? That's because we're not pointing to here. We're actually pointing to somewhere in an off slave. Yes. That's why there's a little bit off there. If we make this even lower, eventually we can find that. So 80, 90 is here, out of the offset. 70, ooh, very small. 5D. 5D will get a segmentation fault. So somewhere here, 60, so it has to be 7 something. Yep. Yeah. So the shellcode basically with a knob start at 6F. That's why after 6F, you always get a flag. And from there, we're supposed to have 1,000 bytes of knobs left, which means so DA, then DB is safe, right? That's like 200 more. So DB is safe. BC, BCDE will work as well. E doesn't work anymore. That's more than 1,000 bytes. Yeah, you can do a little bit of calculation. So this is how we can put that in the environment variable. Let me see if my slide has the next one. Okay, that's what we have today actually. So next week next Thursday, we're trying to put this just in command line argument. A little bit overview of our homework. So homework has been posted. first two questions about the coding convention. Then either one about a little bit reverse engineering and explain the 5 parameters challenge. Then just capture the flag of the overflow, return 1, 2, 3, and the chain. Okay. So not today's class. Today's class will be next homework. So did everyone submit your homework? Okay, cool. Then I guess see you guys. Any other questions? Ready?
Yeah.
Today? Okay, I made a mistake. It should be before the class. Yeah, but I mean, yeah. That's why I didn't say everyone submit. I was wondering why. Yeah, it's okay. I give you extra hours today.